This is Daryl with Hands-On Cisco Training, episode 17. Today we're going to talk about OSPF route redistribution. It's July 2007. On my website I have something new. I have a support Daryl link. Cisco Hands-On Training is free and it will always be free, but I am spending about $500 a year on various hosting expenses. In addition, I also received a request to teach classes on some features that my old 2500 routers don't support. For example, 802.1q or ISL encapsulation sub-interfaces, which are supported first in the 2600 series. So if you feel like helping me out with my expenses or helping me buy some newer routers, go ahead and go to my website, go to the Support Daryl link, and you can donate through PayPal. Okay, let's get into OSPF route redistribution. Here's our map for today. We're going to run OSPF in Area 0 and Area 172.16.6.0, and we're also going to run RIP version 2. So let's go configure our routers. We're starting on the top router today. And I've already configured my IP addresses, but have not configured my routing protocols. Let's test that we can ping. I can ping the middle router, and I can ping the bottom router. So, conft router OSPF process ID 1. And let's see, network. Since I have multiple areas, I'm going to I need to configure my network specifically. So network 172.16.2.1. Don't care bits of 0.0.0.0. Area 0. Network 172.16.1.1. Don't care bits of 0.0.0.0. Area 0. Network 172.16.6.1, area 172.16.6.0. And always important to do the right mem. And let's go to the middle router. Okay, on the middle router, conft router OSPF 1, network 172.16.2.2, don't care bits of 0.0.0.0, area 0, and then we need router RIP version 2, and then network 172.16.3.0, and it's not letting me configure a net mask here. Network 172.16.4.0. Let's see what that showed up in the config. Now you can see, even though I tried to configure the network statement in router RIP so it was just those /24s, 170.16.3.0 and 170.16.4.0, the router did not allow me to do that. With this particular version of iOS, I only had the option to turn on RIP for the entire class B 172.16.0.0, which is sort of annoying. I don't want to run RIP and send RIP advertisements out my serial 1 interface. So the closest I can get to that is doing, in router RIP, I can do passive dash interface, there's a dash there, serial 1. And that way at least I won't talk the routing protocol on that. And let's go to the bottom router. Conf T, router OSPF1, network 172.16.6.2, 0.0.0.0, area 172.16.6.0, network, and then router RIP version 2, network 172.16.0.0. I've already learned I have no choice but to turn it on for the entire class B, and then I'll do passive int serial 0. And that's it with my config. Let's see if my OSPF neighbors came up. Show IP OSPF neighbors. And I've got a neighbor. Let me expand my window here. Show IP OSPF database. And let's see, this is area. I only have one area on this router. This router has area 170.16.6.0. There are two routers in the area, the bottom router and the top router. And so I have two router LSAs. And then I have, so here's my map. I have two routers in this area, so I expect two router LSAs. I have two subnets that are in a different area, so I expect two summary network LSAs, and I have them. Let's go ahead and go to, now you notice what's not in my OSPF database, however, is any routes from the RIP environment. Because RIP is routing and OSPF is routing, but the two routing protocols are not talking to each other at all. In order to have the routing protocols talk to each other, I need to configure route redistribution. So if I were to log into the top router right now and I did a show IP route, I would not see any routes for these four subnets. And let's go ahead and do that now. So here I am on the top router, show IP route. And you can see on the top router, all I see are my three directly connected routes. Because the top router is directly connected to this loopback, the top router is directly connected to this serial link, the top router is directly connected to this serial link, and in fact there's the top router doesn't even need any OSPF information. It's directly connected to all of the OSPF interfaces. Going to the middle router, show IP OSPF database, and this middle router is in area 0. There are two routers in area 0, so I expect two router link state advertisements when I see them. There is one subnet that is not in area 0. This subnet over here is in OSPF, but it is not in area 0. And there is the OSPF link state advertisement for it. I do a show IP route, and I have my connected, I have 3 connected routes. This is one of my serial links. This is my other serial link, and this is my loopback interface. And then I have a RIP route, which is the loopback from the bottom router that I learned via RIP version 2, and I have 2 OSPF routes. One is for the loopback on the top router, which is in area 0, and then the other is for the subnet, the other serial link between the top router and the bottom router, which I learned via OSPF, and it is an inter-area route because it is from a different area. Okay, so everything's working fine except that that my top router can't reach the interfaces in the RIP environment. So what I need to do is I need to redistribute from RIP into OSPF. So let's go ahead and try that. Conf t router OSPF1 redistribute RIP. And there's a lot of options, but one of the options is to just hit carriage return right now. So let's go ahead and try that. End. And it gave me a nice warning here. Only classful networks will be redistributed. One of the interesting things about OSPF, or I don't know that it's interesting, but one of the facts is that by default, when you redistribute from another protocol into OSPF, only classful networks get redistributed unless you tell it to consider subnets for redistribution. So let's look at our OSPF database. Show IP OSPF database. There is no change. There's nothing new. I still have 2 router link states. I still have 1 summary link state. So I don't have anything new in my OSPF database, so I definitely am not helping much here. Conf t, let's try again. Router OSPF1 redistribute RIP. Let's try that subnets keyword. Show IP OSPF database. Aha! Now I have something new. I have a new type of link state advertisement. It is a type 5 external, autonomous system external link state, or external link state. When we redistribute from RIP into OSPF, the subnets keyword allowed us to redistribute these subnets, which are /24s, which are not classful. In classful sense, the classful address block for 172.16 is a /16. So the classful block would be 172.16.0.0/16. Without the subnets keyword, you only redistribute classful blocks. Once we configured the subnets keyword, then the 3 routes that we could see are 2 directly connected and the 1 via RIP. Those 3 routes are all in our RIP routing domain. They get advertised into OSPF as external routes. Let's look at one of them in detail. Show IP OSPF database, hit question mark, and you can see here's all the different type of database entries we can look at. Most of these are different types of LSAs, and there's one for external, which is also a type 5. External, and then I'll just hit return here. Okay, and there were 3 externals. Let's scroll back up. Type 5 AS external link states. Link state age is 89 seconds. It is an AS external link. The link state ID is 172.16.3.0. The advertising router is 172.16.3.1, which is me, because I am redistributing it from RIP into OSPF, so I am the advertising router. The link state sequence number is 80,000,001, which is the first one. It has a checksum. It is a length of 36 bytes. The net mask is a /24. It is a metric type 2. And then there's a note which says that a metric type 2 is larger than any link state path. In OSPF, there are 2 different types of external routes. There are external type 1 and external type 2. And in OSPF, there's a routing hierarchy. You can be in the area, you can route in an area, you can route between areas, you can route external type 1, and you can route external type 2. And a route within an area is always better than a route between areas, which is always better than a external metric type 1, which is always better than an external metric type 2. Type of service is 0. Metric is 20. This is the default metric. In our redistribute RIP command, we had an option to specify a metric, but by default it's 20 for all protocols other than BGP when you redistribute. And the forwarding address is 0000, which means that you forward to the advertising router. And any external route tag information. There are no external tags. Okay, that is that external link state. And then here's another one. Remember, we have 3 external LSAs. Age 89. It's basically the same as before, except it is a different subnet mask. And then let's look at this one. So 172.16.5.0/24 external metric type 2, metric 20. Let me go look at my top router. Show IP OSPF database. There are 2 areas on this router. The first is area 0, where we have 2 router LSAs, and we have 1 summary LSA, and then we have, that's in area 0, and then in area 172.16.6.0 we have 2 router LSAs, and then we have 2 summary LSAs, and then in 172.16.6.0 we also have a summary autonomous system boundary link state. Which is interesting. And then we have our type 5 AS external link states. This is, okay, this is a, I know what this is now. This is our routers. You've heard of area border routers. Area border routers are routers which are connected to area 0 and a different area. This router is an area border router because it's connected to area 0 and it's connected to 172.16.6.0. But there's something else. There's also autonomous system boundary routers. An autonomous system boundary router is a router which connects between an OSPF domain and a different routing protocol. And so router 172.16.3.1, which is the loopback address on the middle router, which is where we're doing our redistribution, is an autonomous system boundary router. So what's happening here is that, and this is interesting, the middle router here is an autonomous system boundary router. It redistributes from RIP into OSPF. The area border router here, which is the top router, it passes along the type 5 external link states from area 0 into area 172.16.6.0. But when it does that, it needs to tell the routers in area 172.16.6.0 where to go to get to those destinations. So it says that if you want to get to 172.16.3.0/24, you go there by going to this advertising router, 172.16.3.1. But in order for the routers in area 172.16.6.0 to know how to get here, they don't know how to get here because this is outside their area. So there's another LSA that the area border router originates, and for each autonomous system boundary router, it originates a LSA for it. So let's go ahead and look at that. Show IP OSPF database and ASBR-summary. Autonomous System Boundary Router Summary Link States. And here it is. And it says that in area 172.16.6.0 there's an autonomous system boundary link state. It's 533 seconds old. It is for link state ID 172.16.3.1 saying, hey, if you want to reach router 172.16.3.1, then to get there, you have to go through 172.16.1.1, which is the area border router. And it has a metric of 64, which is one serial link. So this Autonomous System Boundary Router LSA is a Type 4 LSA. So now we have our first 5 types of LSAs. Type 1 is network, Type 2 is, Type 1 is router, Type 2 is network for the broadcast shared networks like Ethernet. Type 3 is summary, which is an area border router, translates route advertisements into summaries between areas. Type 5 is a route advertisement that is external, an external route, and Type 4 is how to get to an autonomous system boundary router. So in order to use a Type 5 LSA, you need to either be in the same area or you need to know how to get to that autonomous system boundary router thanks to the Type 4 LSA. Let's look at our bottom router. Let's look at our routing table, show IP route. So we start off with our 3 directly connected routes, our loopback and our 2 serial interfaces. And then we have 2 OSPF inter-area routes. This is for the loopback on the top router. And this is for the serial interface on the far side of the triangle. Now this is interesting. 172.16.3.0/24 is for this subnet off of the loopback. And we are on the bottom router over here. So our shortest path to get there is 1 router hop via RIP version 2. However, that's not the route in the route table. In the route table, our best way to get there is via OSPF via the top router. So it is the /24, it is an OSPF external type 2 route. It is a metric of 20, and we get there via the top router. Now, it's interesting for a couple reasons. One reason that's interesting is because that's not our best way to get there. We are preferring the OSPF route over the RIP route because OSPF has an administrative distance of 110 and RIP has an administrative distance of 120. OSPF is a superior routing protocol, so when we learn the same route with the same net mask via OSPF and RIP, we prefer the OSPF route, even an OSPF external route. The other reason it's interesting is we saw that route when it was redistributed. And when we looked at it in the routing table, it had a metric of 20. And now we're 2 hops further away, 2 serial links, each of which have a cost of 64, but the metric is still 20. That is something about OSPF external type 2 routes. The metric that you redistributed at is not changed when you go through multiple hops. The reason is because an external type 2 route is assumed to be so external, multiple autonomous system hops away, that any metric inside your routing domain is insignificant. So the routing protocol does not bother to recalculate the route advertisement. Let's go ahead and change the redistribution to be external type 1. So I'm plugging into the middle router. And I'll do a show run pipe begin router OSPF, and you can see our redistribute RIP subnets. So conft router OSPF1 redistribute RIP subnets metric dash type 1. Show IP OSPF database. And here is my external type route. So show IP OSPF database external, I believe it is, yes. And you can see the metric type is 1, and it is still a metric of 20. It's still being redistributed with the default metric of 20, but our metric type is now 1. So let's go ahead and go to the top router. Show IP route. Now here are my 3 external routes, and they're OSPF. They're now external type 1, and you can see the metric isn't 20 anymore. The metric is 84, which is 20 plus 64. So an OSPF external type 1 metric, you add the intervening hop counts to the metric. I mean, it's redistributed in a metric of 20, and it's not fixed throughout the domain. The OSPF process knows, hey, it's 64. It's a cost of 64 to get to the autonomous system boundary router, and the autonomous system boundary router is redistributing it with a cost of 20. So my total cost to get to the destination is 84. And now let's go to the bottom router. Show IP route. And here you can see the cost of the external route is 148, which is 64 plus 64 plus 20. So OSPF external type 1 routes, you keep on adding the cost throughout your routing domain, but OSPF external type 2, when you redistribute it at a cost, and then you just keep that cost constant throughout the domain. Looking back at our map, the middle router knows how to get to all of the RIP domain because it's part of the RIP routing protocol. And it knows how to get to the entire OSPF domain because it's running the OSPF protocol. The bottom router knows how to get to the OSPF domain because it's running the OSPF protocol, and it knows how to get to the RIP domain because it's running the RIP protocol. The top router knows how to get to the OSPF domain because it's running the OSPF protocol, but the only reason why it knows how to get to the RIP domain is because the middle router is redistributing from RIP to OSPF. That's why we have complete routing information. We're redistributing from RIP into OSPF. We're not redistributing from OSPF into RIP here, but our domain still has full connectivity, and the reason it does is because every router in our environment is running OSPF. Now the top router has 2 ways to get to the RIP domain. It can get there via the middle router or the bottom router, but we're only redistributing from RIP into OSPF at the middle router. We're not redistributing at the bottom router. So let's go ahead and redistribute from RIP to OSPF at the bottom router and see what happens. So conf t router OSPF1 redistribute RIP subnets metric dash type 1. And now let's go ahead and go to the top router. We're on the top router. Let's look at our database. Show IP OSPF database. So in area 0, we have our 2 router link states. We have our summary link state for the one subnet, which is in area 172.16.6.0. We have our summary autonomous system boundary link state this is for the bottom router, and it's being advertised. See, here's the bottom router with 170.16.5.1, and here's the top router with 170.16.1.1, and this is in area 0. So the bottom router is an autonomous system boundary router, and our area border router knows that, so it generates the autonomous system boundary summary link state for the bottom router and injects it into area 0. And then in area 170.16.6.0, we have our 2 router link states. We have our two summary link states for the two subnets that are in area 0 that the area border router sends into area 172.16.6.0. We have our summary autonomous system boundary link state, which says, hey, if you're in area 172.16.6.0 and you need to get to the autonomous system boundary router 172.16.3.1, you can get there through the area border router at 170.16.1.1. And then we have a total of 5 autonomous system external link states, which are shared among all of our areas. And 2 of them are originated by the middle router, and 3 of them are originated by the bottom router. Let's look at our routing table. Show IP route. And the interesting route is the route of the subnet on the far side, the serial subnet on the far side. We can get there via the middle router or the bottom router with equal cost of 64 on this link or this link. We know that. Let's see if the routing protocol knows that. And the answer is yes, the routing protocol does know that. It has, for the route 172.16.4.0, it knows that it can get there via the middle router or the bottom router. So that's good. And then for 172.16.5.0, it knows that the best way to get there is via the bottom router. And for 172.16.3.0, it knows that the best way to get there is via the middle router. And then we have our directly connected routes. Now let's go ahead and do an experiment. I am going to the bottom router, conf t router OSPF, router OSPF process ID 1, redistribute, rip, subnets, metric type, metric dash type 2. Now our default metric is 20. So now I go back to the top route, and what's interesting is that for that subnet in the middle, we have 2 ways to get there, via the middle router and the bottom router. And via the middle router, it is an OSPF external type 1 route with a metric of 84, 20 plus 64. Now let's look at now if we looked at our OSPF database, we know that the route to 172.16.5.1/24, we know that route is, the route to 172.16.4.1/24, we know that route is metric of 20 because it's OSPF external type 2. Show IP OSPF database. Here are the external routes. Show IP OSPF database external 172.16.4.0. And you can see the metric is 20. And we know because it's external type 2, we don't add anything to the metric. So what's going on here? We have our 2 routes. We know how to get to this route via 2 different ways. One is an OSPF external type 1 with our metric of 84, and one is our OSPF external type 2 with a metric of 20. Well, you would think that the metric of 20 would be preferred over the metric of 84. But OSPF has a strict hierarchy. OSPF external type 1 is always better than OSPF external type 2. And in fact, Well, here is the OSPF external type 1. You can see we have two entries for 172.16.4.0. Show IP OSPF Database external. And let's look for it. Here is the entry for 172.16.4.0, which is external metric type 2, and it says right there it's larger than any length state path. So OSPF external type 1 is always preferred to OSPF external type 2. Okay, that concludes today's discussion about OSPF redistribution.